Hey, my name is Jonathan Helm, and in this video I'll show you how to perform a simple linear regression in R. For this video I'm going to use the salary data.csv dataset, so if you want access to that then you can go find it on my website, and the intro video to this playlist will show you how to get that dataset. So I'm just going to start by opening up R. So I'm going to scroll to my applications and I'll open up R on my computer. The console will open up and I'm going to open a new document, or I'm just going to open a new editor in R. So first things first, we need to read the data set into R. For this one, I'm going to use the read.csv function. And so I'll right click the data file. I'm going to copy the path to that data file. Paste it into the editor. I'm going to add a // and I'm going to copy in the name of the dataset. I'll highlight and run this. I'm going to take a look at the top of the dataset. So I'm going to highlight and run that. I'm going to get the first 6 rows of my dataset, and then I'm going to open up the Excel sheet that contains my data, the actual data file, and just compare it to the values that I see in R, right? So again, my first step is just to read in the data set, and it's really best practice to make sure that whatever you've read into R is actually the same as what you see in your raw data file, right? So I see that there's an ID, and the values of ID look like they match up. The variable for salary and the salaries matching up. Number of publications are matching up. Scroll over, years on the job is matching up. Grants is matching up, right? And so I feel fairly confident that I've correctly read the data set into R. Now in this situation, we start with simple linear regression. The simplest model that I can fit would be an intercept-only model, right? So when we just have an intercept and we actually don't have any predictors. I'm going to call this model.01. Right, I'm going to set that equal to a function called LM, and this stands for linear model. Right, we're performing a linear model. The first argument of that function is going to be the form. So let's say in this example that I'd like to predict salary. Okay, so I'm just going to write salary here, and I have a tilde function. I'm going to add a 1. Okay, and what that means is that I'm going to predict salary from a constant, right, from a constant 1. Now, if you remember from our regression model, the intercept, right? The intercept actually looks like this, like you have b0 times 1, right? So there's actually 1 out here, and we often don't write it, right? We often don't write this 1, right? And then we might have like b1 times some other predictor plus b2 times some other predictor, and so on, right? So in this case, I'm just going to estimate the intercept, okay? And normally what I would do in R is I write out what each of the predictors are, and I'll show you an example of this in just a second. Okay, so I would include something like number of pubs, right? Number of pubs, or something like years on the job. Okay. Now we don't actually type out the b0, b1, and b2 because R knows that it needs to estimate coefficients for each of the predictors. So in the case of the intercept-only model, right, we just leave the 1 in there, and that's all we have. Right? We just leave the 1. I need to tell R where these variables are, so I have salary, and it needs to know where those variables are, and I say that's in a data set called data, right? So I read in the data set up here, and when I read in those data, I saved it into an object called data, right? And you could have called this my data, salary data, or anything that you wanted. Okay, but the point is that this is the name of that data set, so I need to put this over here, right? So I have data equals data. You could also write data equals my data, or data equals salary data, if that's what you used up here. Again, I have one other thing that I want to tell R, and that's this na.action. Right? That's asking what to do with the data, and I'm always going to type na.exclude, right? Which is going to perform listwise deletion for us. Okay, so really what we're doing is we're using the lm function, right? We have the lm function. We're saying to R we want to predict salary using just an intercept. Okay, the variables that we're using, they're in the data set called data, and if you run it into any missing values to perform listwise deletion. Okay, and you're going to perform that linear regression, and all of the output that you get, I want you to store all of that into model.01, right? So it's a new object that I'm creating, and that object will contain all of the output from that model. So I'm going to highlight and run this. Right? I don't get anything back. Of course, often what we want to be able to do is to see that output, right? And to observe it, I'm going to use the summary function. Right? So the summary function is used often in R just to give summaries of different types of objects or outputs. In this case, the summary function is really useful for looking at the output from a linear model. So if I highlight and run that, you'll see that I'm going to get the estimate of my intercept here. Okay, this is my estimated intercept. Of course, this refers to the mean of salary, right? This is my prediction of salary, but I don't have any other predictors in the model, right? And so it's my best guess. Okay, so my best guess salary is 76.133, or about $76,000 a year. Okay, now let's say that I want to predict this from another variable, right? So actually performing the simple linear regression. So this is an intercept-only model that doesn't have any predictors. Now I can do model.o2 equals lm, and I have salary. I have 1 plus, and I'm just going to add in one of the predictors. So to take a look at the top of the data set, let's just do number of publications. So I have number of pubs. I need to tell R where those variables are, and I still have the NA action equals NA dot exclude. Okay, so it's very similar, right? It's very similar to the first model, but the only thing I'm doing is I'm adding in another predictor, right? So if we wanted to be a little more explicit, like the intercept would go here, and the slope would go here. Okay, but R knows that it's going to estimate those coefficients, so we don't actually write that out when we use the function. Okay, and we put just one for the intercept, and then we put the next predictor, and so on. Okay, so I can highlight this, and I can run it. Again, I'm going to use the summary function to look at model.o2. Okay, now I'm getting an estimate of the intercept and an estimate of the slope, right? And so the intercept is, this is the predicted salary that you have if you have 0 publications on average per year. And this slope reflects the amount of change in salary for a 1 unit increase in number of pubs, right? So if your average number of publications per year increases by 1, we expect your salary to go up by $5,000 a year. Okay. We get p-values for each of these. Right, we're also getting an R squared, so the R squared about 5% of, in this data set, about 5% of the variability on salary is accounted for by average number of publications per year. Of course, we get an adjustment on that for sample size. And we also get a p-value, probability value for this multiple R squared, right? And again, the p-values are interpreted as, assuming that the null hypothesis is true, right? In this case, the null hypothesis is always referring to that these estimates actually equal 0. So assuming that that's true, what is the probability of getting this value with this sample size? And this is the corresponding probability. And by this value, I mean this value or more extreme. Okay, now one of the other useful functions that I want to point out is this ANOVA function, right? So oftentimes when we're performing regression, we want to compare 2 models, right? And we want to understand if the change in the R squared is significantly different from 0. Right, so I can do ANOVA model 1, comma ANOVA model 2. And what this is doing is it's actually going to calculate if the change in R squared across these 2 models is significantly different from 0. Models are not nested. Models are not fitted the same size. This is really interesting. This is an error that you might run into. One of the reasons why the data sets are different across these 2 examples is because salary up here has complete data, but number of publications down here only has missing data. So it's performing listwise deletion on this data set, and therefore we have fewer observations. So one way I can get around this, let me think about the easiest way to do this. Let's create a data set. Don't usually encourage doing this, but just for fun, we'll create a data set that performs listwise deletion on all variables. So I'm going to call this data no NA. And if I do na.omit that function on data, what it'll do is it'll perform listwise deletion across all variables. So if there's missingness on any value for a given row, it'll remove the whole row. So we'll just do that, and then what I'll do is I'll make data no na here, and I'll also do data no na here. So that way they're performing the same analysis. They're using the same data set across the 2 analyses. So I'm getting a slightly different estimate for the intercept, of course, because there's been some rows removed. And I'll do the second one here. for model O2. I'm going to get a slightly different intercept and slope. And then if I do the same nova across model 1 and model 2, now I should get the difference, right? And of course, this difference, there's a couple of things that it's going to directly match. This difference will directly match the r squared that we see in model 2. And the reason is because model 1 doesn't have any predictors, so the r squared is 0, right? It's comparing it to 0. Right, so the change in r squared from model 1 to model 2 should be the exact same as the r squared that we just see in model 2. Okay, so we're getting this multiple r squared value, and the p value that it corresponds to should be the same in this exact situation. It should be the same. Right? And moving up, the other thing I was going to point out, so the p values are the same across these two. Yeah, that's it. Oh, no, the one other thing. Since we're including one predictor, the change in the r squared here will also directly correspond to the p-value for that one predictor here. Right? So the change in the r squared is the same as the one predictor that we added in this case. Now if we added multiple predictors across two different models, then of course the change in r squared corresponds to all of its predictors, and it wouldn't have that one-to-one comparison. But in this case, since we're just adding one predictor, the number of publications, it's going to have the same p-value as the change in the r squared from the model without number of publications to the model with it. Okay, so just some properties to kind of be aware of. Okay, so thank you so much for watching. Let me know if you have any other comments or questions. You can add comments below to the feed, or you can also email me directly at jonathanleehelm@gmail.com. You can also follow me on Twitter at jonathanleehelm. And if you haven't subscribed yet to the YouTube channel, please go ahead and do that. I look forward to hearing any feedback that you have, and thank you so much for watching.